Hydraulic elevators are supported by a fluid-driven piston at the bottom of the elevator. The piston pushes the elevator up. The machine room for hydraulic elevators is typically located at the lowest level adjacent to the elevator shaft. Compared to traction elevators, hydraulic systems are easier and more economical to install, less expensive to maintain, but they are used for low-rise applications, typically up to 5 stories, and travel at a maximum speed of 150 to 200 feet per minute. There are multiple types of hydraulic elevators: holed, holeless, and roped. This shows a conventional holed hydraulic elevator that has the hydraulic cylinders placed inside a drilled hole in the ground. An elevator machine room located adjacent to the hoistway on the main lobby level is required for the hole type. The maximum travel distance of a holed hydraulic elevator is approximately 60 feet. Holeless hydraulic elevators typically have a piston on either side of the cab, eliminating the need of a hole drilled into the ground and the risk of oil contamination. However, they require a slightly larger hoistway than holed elevators. This shows a single-stage holeless hydraulic elevator, which is equipped with one piston, goes up and down without telescoping. They are easy to install and are the most economical choice. Single-stage holeless elevators are popular for a two-stop arrangement up to approximately 20 feet of travel distance. This shows a telescoping holeless elevator with 2 pistons in 2 stages. Some models can have up to 4 pistons, each traveling inside each other. Telescoping holeless pistons typically allow up to 50 feet of travel distance. Telescopic pistons can also go in-ground to reduce the depth of the hole required, but they can be more costly than single-stage models. Roped hydraulic elevators use a combination of ropes and pistons to move the elevator. The pistons raise and lower the pulleys, and therefore the ratio between the piston travel and the cab travel is 1 to 2. The maximum travel distance of a roped holeless elevator is about 60 to 70 feet, and it can be less expensive to install than a traction elevator serving the same number of stops. This is the plan view of 2 hydraulic elevators with side opening doors. This shows an elevator machine room where the hydraulic fluid tank, pump, controller, and main disconnect switches are located. For hydraulic elevators, especially the ones with a larger load capacity, it is best to place the machine room on the first floor adjacent to the hoistway or as close as possible. A machine room is usually required for a holed hydraulic elevator, but may not be for holeless systems. Machine roomless hydraulic elevators do not have a dedicated room to house the hydraulic tank and pump, which are installed in the elevator pit instead. The controller is normally located on a wall near the elevator on the bottom floor. Machine roomless hydraulic elevators save space and cost. Traction elevators are the most common type of elevators. The cab of a traction elevator is raised and lowered by steel cables in the pulley system. They use a counterweight to offset the weight of the cab and occupants. This reduces the load for the motor, making it more energy efficient than hydraulic systems. Traction elevators can be geared or gearless. Geared traction elevators have a gearbox that is attached to the motor. It drives the wheel and moves the cables. Geared traction elevators are capable of traveling up to 500 feet per minute. Gearless traction elevators have the wheel attached directly to the motor. They are capable of traveling up to 2,000 feet per minute. This shows a traction elevator with a machine room above the roof to accommodate the motor and the control equipment. Machine roomless traction elevators do not have a dedicated machine room on top of the hoistway. Instead, the hoisting machine is installed either on a sidewall of the hoistway in the override space or on a sidewall at the bottom of the hoistway. The control unit is usually installed on the top floor above the seating adjacent to the elevator shaft. Most machine roomless elevators are used for low to mid-rise buildings, usually serving up to 20 floors. Without a machine room above the roof, these elevators eliminate the need of a penthouse on the top of the elevators that might be visible from outside. This shows the plan view of two traction elevators with center opening doors. They have counterweights in the hoistway. This shows the machine room on the top, which is typically larger than the hoistway below. This diagram summarizes elevator types and the building heights that they are typically serving. This is for general recommendation only. Designers need to refer to elevator manufacturers' data for detail. Elevator manufacturers usually offer four types of doors. Single-speed side opening, a common elevator door style that features a single panel entrance rather than splitting in the middle. It tends to be the most cost-effective option and is often found in small elevators. Single-speed center open. As another common elevator door type, a single-speed center opening door is made of two panels, sliding in two directions. Because it has two doors, it requires a larger car width to temporarily store the doors on both sides. This option is a standard type for elevators with a wide range of capacities. Two-speed side open. This is made of two panels that stack into each other and slide in one direction with different speeds. It is a popular option for freight elevators as well as passenger ones. Two-speed center open. This option combines the features of the last two styles. It is made of four panels that open to both sides. It is commonly used for buildings that need to accommodate a large number of people or objects, such as hospital beds. Here are some recommendations for the lobby design. The depth of the lobby serving a single row of elevators shall be at least the depth of the elevator cars. The depth of the lobby serving two rows of elevators facing each other shall at least double the depth of the elevator cars. When installing multiple elevators in a row, do not exceed 4 elevators in the same hoistway. If more than 4 elevators are installed, place them in separate hoistways. Zoning is to divide elevator service into several zones and assign a group of elevators for each zone. Office buildings of more than 20 stories are usually zoned in order to reduce the wait time. In the multi-zone example in this diagram, the building is divided up into 3 zones, each serving 5 floors. Sky lobbies are usually designed in skyscrapers, where people can change from express elevators, also known as shuttles, which come from the ground level lobby and stop only at the sky lobby, to a local elevator that stops at the floors above the sky lobby. The sky lobby example in this diagram shows that 2 shuttles lift people to the sky lobby level, where there's another bank of local elevators unconnected to the ones below the sky lobby. Although simple rules of thumb are available, such as 200 to 250 occupants per car in office buildings and 120 to 150 rooms per car in hotels, a more comprehensive method is introduced here with an example. This method is primarily based on the works of Barney and Al-Sharif. The process is illustrated in this diagram. The details of the example building are provided here. Some of the terms will be explained later in the design process. Step 1 is to determine building net square footage. If net square footage is not available, It can be estimated by multiplying the building gross square footage above the ground floor with the net to gross factor suggested in this table. For office buildings, this factor is 75%. Step 2 is to determine population. This table shows the criteria of estimating building population for the purpose of elevator planning based on the building's net square footage. Step 3 is to determine handling capacity, HC. Handling capacity is the maximum number of passengers that need to be handled in a 5-minute period. For an office building, this typically occurs early in the morning when occupants arrive at work. Handling capacity can be estimated by a ratio expressed as a percentage of the building's population. This table shows the minimum percentages for estimating the handling capacities of common building types. Step 4 is to identify building height. Because the elevators are only serving the floors above the main lobby, the number of floors N in an elevator system only includes the levels above the ground floor. The floor-to-floor height, DF, also defines the rise of the elevators. Step 5 is to select a car and determine its passenger capacity, P. The load capacity of passenger elevators typically ranges from 900 to 2,000 kilograms, approximately 2,000 to 4,500 pounds. The rated speed can range from 0.5 meter per second to over 20 meter per second. This table lists the rated passenger capacity and average capacity of common load capacities. The latter is normally 80% of the former. Step 6 is to determine round-trip time, RTT. Round-trip time is the time in seconds required by an elevator to complete a full cycle in the building, starting from the time the car leaves the lobby to the time the car returns to the lobby after stopping at the floors called by passengers. Barney and El-Sharif developed an analytical calculation method to estimate the elevator round-trip time based on 4 parameters: N, the number of floors above lobby; DF, floor-to-floor height; P, average passenger capacity; V, rated elevator speed. Based on this method, a series of graphs are created to estimate the RTTs based on various combinations of the 4 parameters, N, DF, P, and V. This shows one of these graphs with the parameters of the example building. RTT is estimated at 121 seconds from this graph based on the above 4 values. Step 7 is to determine 5-minute handling capacity per car, small h. This metric represents how many people can be handled with a 5-minute period by one car. It is determined by 2 parameters: the average passenger capacity, P, and round-trip time, RTT. Step 8 is to determine the number of cars required, L. The number of cars required for a building should meet 2 requirements established for the project. 1, the targeted quality of service, and 2, the handling capacity calculated in Step 3. Here, the number of cars L is first estimated according to the second requirement by using this formula. Step 9 is to determine interval. Interval I, or lobby dispatch time, is defined as the average time between the departure of cars from the lobby. Interval determines the wait time at the lobby and therefore is a metric indicating the level of service quality. Elevator interval is calculated by dividing round trip time by the number of cars estimated in step 8. Step 10 is to confirm interval. The last step is to confirm if the current interval meets the targeted level of service quality. This table lists the recommended elevator intervals for common building types. If the interval calculated in step 8 based on handling capacity does not meet the targeted level of service quality, increase the number of cars, load capacity, and/or speed, and repeat the previous steps necessary to recalculate the interval time until the interval falls within or exceed the targeted range indicated in this table.